Great. So Dingtong, can you share your screen?
Sure.
So again, the housekeeping rules, please contribute in the chat box with all of your thoughts, questions, answers, and let's just keep that discussion. That's the whole purpose of, sharing our research, learning from each other as well. Thank you. Over to you, Dingtong.
Sure. Yeah, thanks for the introduction. I mean, I think I will try to make the presentation shorter because I feel we may overrun for the previous session and we still have 5 presentations to go.
Thank you.
So
Just briefly introduce yourself. Which university and what are you doing? Thank you.
Yeah, the
Orji.
interesting thing is I only received the email about sending a brief introduction to the host this morning, and I didn't see the email until the last minute.
All good.
Yeah, sorry about that.
Over to you.
I will do So my name is Dingtong Yang, and I'm now working as a postdoc in the Singapore MIT Alliance for Research and Technology Center, and I graduated as a PhD from the Civil and Environmental Engineering departments from the University of California, Irvine. And this is also a joint work with my previous supervisor, Michael Highland. And today, the topic we are going to talk about is electric vehicle in urban delivery fleets. How far can they go? So, So for a brief agenda for today's presentation, we try to do a brief introduction. In the introduction, we will talk about the motivation and the background of this study. And then I will briefly introduce our research questions and the methodology, what framework and what optimization method we're using. And then I will give a more detailed study of a numerical case study, which use the real world data in the Southern California area. And then we come to the conclusion. So what's the motivation of this study? In the early 2020, the state of California has issued a mandate that they would like to see a 100% zero emission vehicle adoption by the year for a dredge truck by the year 2035, and also medium and heavy duty on-road vehicles in the state by the year 2045. And I would say this is really ambitious mandate. And here, a definition about the zero emission vehicle, it actually refers to the zero tailpipe emission vehicle. Because for the zero emission vehicle, if we use either hydrogen vehicle or EV, it's unavoidable to have environmental impact during the production procedure. And to fit this regulation, we will see a transition period where the logistic companies they're going to use mixed fleets for their activities. So here we would when we refer to the mixed fleets, we would like to mention it mainly refers to use adoption of electric vehicles and conventional fuel vehicles. And therefore, the question comes for the logistic company is what's their plan during the transition period for adopting the vehicles in their mixed fleet. And this is in our motivation to do this study. Then I would like to do a brief comparison between the conventional fuel vehicle and electric vehicle. Since for this study, I'm referring to the business that the logistics company is doing for last mile delivery. So we take the very typical last mile vehicle used by Amazon and some other logistic companies for their delivery. And the example we use here is a Ford Transit. So, if we compare a conventional fuel version of Ford Transit and electric version of Ford Transit, we see that the average fuel cost between the two is about 25 cents per mile for the conventional fuel vehicle and only around 10 cents for the electric vehicle. And this number will be different across the states in the USA because the electric both the gas price and electricity price are different across the country, and this is a national average. with respect to the CO2 tailpipe emission for the conventional vehicle, it's around 19 pounds per gallon. However, for the electric vehicle, it's just a 0 tailpipe emission. And however, the CFV has more advantages in the range, refilling time, and even the retail price. We see that for the range, it has a 400 range comparing to the currently only 115 range for the electric version of the Ford Transit. And while for the refilling time, it's just very quick to pump gas to the tank, while it's slow to charge the electric vehicle. So for this study, our research question is mainly regarding to the scenario where companies in their last mile logistic delivery industry, and they would like to adopt EV during the transition period. However, the EV has advantages in the cost, while the battery technology is not as good as the conventional fuel vehicle for the range. However, we also assume that the EV range will advance with time. And the research question we would like to answer are threefold. The first one is that for a logistic company, how could they design the fleet mix which minimize their operating costs when they would like to adopt both EV and CFV for their last mile delivery? And for the policymaker, what kind of policy or incentives they could provide or regulate to encourage the usage of EV. And also we would like to see with this change alongside the EV range advancement, what would be the impact for the society, especially on the environmental perspective. So here is our framework for this study. So we collect the input for the logistics companies, such as their demand and their depot location, service region, and road network. And also we have the CFV and EV range, especially the EV current range and future range. And also we collect the current cost for conventional fuel vehicles and electric vehicles. And also we consider the labor cost for the drivers. So we have the driver wage, and also we consider the traffic conditions, such as something like congestion. And after we collect these inputs, we're gonna solve a optimization problem from the logistic company perspective that minimize their total operating cost of adopting the mixed fleet for last mile delivery. And in this scenario, we're going to enumerate all the reasonable fleet size and the mixed combinations for the companies. And then we solve a fixed, I think it's the fixed fleet size and a multi-vehicle routing problem for the logistic company, which minimize the total cost. And then we determine the optimal fleet and mix by comparing the different scenarios that we enumerated earlier. And then we make suggestions for the logistic companies for which fleet size to take. After the optimization, the major output we would like to see is the total cost of adopting the mixed fleet, and also the fleet size and mix, and also the VMT, because the VMT gonna lead us to the discussion of how the environmental impact would be. So here is a brief overview of what of the vehicle routing problem we are solving. In objective function, we try to minimize the total cost, which include the labor cost, electric vehicle cost, the conventional vehicle cost. And on the constraint, we have the conventional routing constraints and range constraints for the EVs, for both the EVs and conventional fuel vehicles. And also we have the time window constraints. And we solve the problem by the Google OR tool, since it is NP hard and Google OR tool applies the heuristic and solve the problem really fast. And in a case study here, I would like to talk about, we choose an area of the Los Angeles and Orange County in the Southern California area, in which we select one depot and then 69 delivery nodes. And within the delivery nodes, there are 20 to 30 delivery locations, which means the vehicle which means each node actually represents a small area or neighborhood that the delivery vehicle will go through. And the objective is to minimize the total delivery cost. And here are the parameter settings we have for the study. And one thing I would like to emphasize here is for the cost of EV and cost of conventional vehicle, we are talking about the costs that include both the operating cost and the purchasing cost depreciated on a per mile basis, which actually means to simplify the calculation, we try to do a per mile depreciation of the purchasing cost based on the average operating mileage of the CFV and EV. And we, under the current situation, we have an estimation of the cost of EV at $0.25 per mile, while the CFV doubles the cost. And we set the range of EV starting from 80 miles until 200 miles. And we set the mileage of the conventional fuel vehicle at 300 miles. And to calculate the travel distance between the nodes and the delivery locations, we use the Google direction tool, and we choose a 12 p.m. Tuesday time to generate the travel time. And after the base scenario, I also would like to introduce two sensitivity analysis here. In one, we just change the EV cost because the cost of EV will impact the adoption of the mix of the fleet significantly. And the second, we would like to see what if we change the number of depots from 1 to 2, which means we're adding more depots or distribution centers in the area, whether that would help the adoption of EV. So in the base scenario, the first result we would like to see is the minimum cost fleet. From the result, we can see that as the as the EV range increases, and it's intuitive that the number of EVs in the fleet will increase, but with a nonlinear trend. This is because the nonlinear trends comes actually from the diminishing of return. So at the beginning, you have the range increase, and you will see a large increase in the EV percentage, but while when it comes to the later stage, you won't see that effect. While the fleet size decrease in the meantime, and this is also very intuitive, since the EV range increase, it can serve more locations. And we would like to mention two important EV range points that's in the figure here. The first one is the 100-mile, which represents the current technology. And under the current technology and the current cost structure, it's the most optimal for the logistics company to keep 1/3 of their fleet electrified. However, when the EV range increases to the 180-mile range, the entire fleet can be electrified, and it's also the optimal solution for the logistics company. And when we compare the total cost and total mileage, total vehicle miles traveled here, we see that the total cost will decrease gradually as the EV range increase. And when the fleet is fully electrified, the total cost is reduced by around 14%. And the total VMT increase, however, the total VMT increased slightly as more EVs are used until the fleet is 100% electrified. And then we could see a small drop with more EV range. Yeah, here it shows the trend. And in the base scenario, we also do one more test where if say the policymaker would like to require a 100% EV fleet, what's going to happen here? So the findings here is that under the current technology, which the EV range equals 120 mileage, we cannot achieve 100% EV fleet under the current technology. However, when the range slightly increased to 140 miles, the fleet can be fully electrified, but we would see the total cost is not optimal, and it's about 20% higher than the optimal fleet mix. And also we will see the fleet size is much larger than the mixed fleet. And as the EV range increase, both the fleet size and cost decrease rapidly. Then in the study, we do a sensitivity analysis where we try to change the cost of EV to see how that would impact the adoption. So we take the two EV range, the two representative EV range. One is the current technology 120, and one is the EV range which right before the 180, which is the fully electrified scenario, which is equals the 160 scenario actually. So here, in this scenario, we see that under current EV technology, EV range technology, when the EV cost is the same as the conventional fuel vehicle cost. And if we move left-hand side, we will see the EV cost decrease. We see that when the EV cost drops from 0.5 to 0.45 per mile, we will see a huge lift in adoption of the EV in the fleet mix. However, when we move further left, even we move from the 0.45 to 0.2, the percentage of EV in the mixed fleet won't change significantly. And a similar trend has been shown in a figure on the right-hand side for the EV range equals 160. And also, when we compare the vehicle mileage for the different costs, we can see that when we move left forward, the VMT increase slightly because when the EV becomes cheaper, more EVs would be used. However, due to the shorthand of the EV, the EV have to travel longer distance to serve the area, and it's similar for both scenario 120 and 160. However, the vehicle miles increase doesn't indicate the total emission would increase. We do the comparison between the two scenarios of 120 mileage of the EV range and 160 mileage of the EV range. We see that for the 120, when the EV cost decrease to 0.2, we have more EV use, and we will see a 24% of cost of emission reduction, of overall emission reduction. And when the EV range reaches 160, when the EV cost becomes only 0.2 comparing to the 0.5 of the CFV cost per mile, we will see a 50% reduction in the total emission. So if we combine the findings from the previous 3 slides, we will see we could the range limits. The range limitation is actually the bottleneck for EV adoption. And also subsidizing the EV cost may not achieve significant improvement. And in the next sensitivity analysis, we introduce a new depot in the area. We see that the one depot serves a sub-area, another depot serves another sub-area. And we also compare the minimum cost fleet with the base scenario, and we see the base scenario here. We see that under the current technology, 90% of fleet can be electrified if the logistics company has 2 depots, and it will be fully electrified only at the 160 mile. However, when setting up the new depot, the logistics company need to think about the trade-off between the cost of operation and the cost of setting up the new depot. And for the cost, we see a drop when we have 2 depot scenario, and the cost saving for the 2 depot scenario is about 5% to 13% depending on the EV range. And with respect to the VMT, it's 2 to 12 smaller for the 2 depot scenario. However, the 2 depot scenario use more EVs, so it significantly reduced the tailpipe emission. To come to the conclusion, first we make the summary of all the findings. Mainly, we see that under the current technology, the logistics company can only electrify around 1/3 of their vehicle without hurting their profitability. And keeping the same cost, when the EV range reaches 180 miles, it can be fully electrified for the logistics company. And the third findings is adopting EVs does not reduce VMT significantly, since the EV is short-handed and it needs to travel more distance for the service. However, it will reduce the overall emission significantly. And reducing EV cost does not increase the EV percentage significantly if the policymaker would like to consider subsidizing the logistics company for EV adoption. And if the company would like to increase EV percentage, they need to think about reconfigure their service network, adding more depots, and it's an option. And the implications for us is the range technology is still the bottleneck for large-scale EV adoption in the last-mile delivery industry. And for policymakers think about subsidizing EV usage, it is important to know that the current cost difference between the CFVs and EVs. If the EV cost overall is as high as CFV, subsidizing EV at early stage would encourage EV adoption. However, the effect diminishes as the subsidized increase. And for companies think about adopting EV, redesign the service network would lead to a large proportion of EV adoption in the service. However, they need to think about the trade-off existing between the facility and land costs and the operating costs. And this would also be a future study of for us. And then we come to the Q&A session, and thank you for attending my presentation. And this paper is a published paper in Transportation Research Part B. And if you have any questions, you are welcome to send me an email.
Thank you, Ding. Thank you so much. It was actually very interesting research, and definitely I will check that out. I wanted to just to ask whether you have published or not. So because we are kind of short in time, I encourage everyone to ask your questions in the chat box. I may actually have a few questions, Ding, for you. So let's if you don't mind, let's just go over to the next presenter, Lynn. And Lynn is a PhD student in transportation engineering at the University of Texas at Austin. And her research focuses on shared autonomous electric vehicles and charging infrastructure planning. And she's currently working on the co-location of public and private charging stations for the new shared autonomous electric vehicles to be operational in Austin, Texas area. So, Aline, over to you. Yeah, please share your screen, and if you keep your presentation like for 20 minutes, then we will have a few minutes for the Q&A. But again, I encourage everyone to ask your questions in the chat box. Thank you. Over to you.
Can you see my screen?
Yes.
Okay, cool. Thank you all for joining this presentation. I'm Lin Su, a PhD student at UT Austin. So the topic I will be presenting today is about the charging infrastructure planning. Specifically, I have introduced the public-private partnerships when siting and sizing the charging stations. This involves co-locating the privately or fleet-owned charging stations with public charging stations to serve the increasing charging need from the fleet EVs and household EVs. I will also explore the impact of this co-location strategy on the operational performance of both the fleet and the charging stations. So recently, with the blooming electric vehicle EV adoption and the growing car sharing membership have contributed to reducing the greenhouse gas emissions. Alongside those developments, many ride-hailing companies are expanding the benefits of the shared autonomous vehicles through the electric fleets, that's SAEVs. Waymo in the San Francisco and Phoenix, Cruise in the San Francisco, and Didi in China are already selling rides. Zwift, Neo, and other companies will be in the market soon. But the main concern for EV is always the range anxiety. The charging station operators like Tesla and ChargePoint, or even some SAV operator like Cruise, have been installing the charging stations for or adding the charging ports across the US, EU, China, or beyond to meet the rising charging demand. However, the fleet-owned charging stations charging infrastructure is often regarded as private infrastructure. The fleet managers face additional siting challenges of cost and access if they do not not make their ports available to the public. As many cities, they provide their subsidized for the charging station open to the public. In addition, many researchers have suggested that encouraging the collaboration of public and private stakeholders is key in improving the charging access for all EVs at a lower cost. So this research used the Austin area as a case study to address the growing demand for charging infrastructure from the expanding SAEV fleet and the household EVs. The SAEV fleet in this study is assumed to be operated within an 81 square mile geofence focused on the central business district. Using the agent-based model Polaris to conduct micro-simulation across the Austin area in a single day, we seek to site and size the public-private charging stations at lower cost and shorter fleet detours while illuminating the performance attributes. The table here shows the key simulation variable used in the Polaris model with their assumed values. So the passengers who choose the ride-hailing service over alternative modes like bus, walk, bike will exclusively use the SAEVs. An SAEV that is within the 10 minutes wait time will be matched with rider requests. A total of 200 SAEVs are expected to be modeled within the geofence area with 250 mile range. When an SAEV's state of charge, the SOC, is below 20%, it will be assigned to get charged. So considering the battery health, the charging process will be cut off once the SOC reaches 80%. When the SAEV is sent for charging, if the distance to the nearby available charging station exceeds 5 miles, then a new fleet-owned charging station will be generated strategically with 3 default DC fast charging plugs to meet the charging demand. And each charging station can only accommodate a maximum of 20 plugs. The table below outlines the scenario settings. Two types of EVs, SAEV and household EV, are modeled against their accessibility to different charging ports. Under the separated scenario, the fleet-owned charging stations are exclusively serving the SAEV fleet, while the household EV can only get charged at the public charging stations. The semi-share scenario offers a household EV additional access to the fleet-owned charging stations. Additionally, those charging stations will be flexibly placed wherever it was needed, considering demand from both household EV and SAEV fleets. In the third scenario, the co-located public-private charging stations grants maximum access to the chargers for all kinds of EVs. Unlike the second scenario, the model here will prioritize locating the fleet-owned chargers alongside the current public chargers to achieve the cost sharing and cost sharing. The left flowchart here describes the model framework for the heuristically sited charging stations. The framework mainly consists of two major parts: the SOC checking, highlighted in blue, and the charging station site selection, and capacity determination, highlighted in green. As EV move along the network inside the Polaris, their SOCs and available ranges are updated continuously. When EVs require charging, the model starts searching for the accessible charging stations within the maximum distance considered for charging. That is 5 miles in this research. If no accessible charging station is found, then the heuristic will cite a new charging station at current location with default 3 DC fast charging plugs. Otherwise, the availability of the charging station will be further examined. When the queue length at an EV charging station exceeds a predefined threshold, but the charging station still has available spots to house additional plugs, then a new plug will be added to the current charging station to support charging. Otherwise, a new charging station will be generated to fulfill this charging demand. The generated charging station and their outfitted plug counts under 3 scenarios are shown in the left. So under the separated scenario, many fleet-owned charging stations are concentrated in the downtown Austin and west to the UT Austin campus. So those locations are primarily shopping and dining centers, schools, and city parks. Due to their land use characteristics, which are typically associated with recreational purpose and dense job opportunities. So there is relatively high demand for ride-hailing service. After incorporating the household EV charging needs, you can see the charging station size under sharing scenarios extend further into the residential areas and along freeways. In the co-located scenario, there is no additional charging stations are generated, which potentially saves a large amount of the installation cost. Instead, 115 fast charging plugs are added to 23 existing public charging stations to enable 200 new SEVs while also serving the household EV charging demand. The SEV fleet performance under 3 testing scenarios is summarized in the table below. So under the co-located scenario, the SEV fleet performs slightly better than the other two in serving more trip requests. On average, each SEV travels around 313 miles per day and serves over 92 requests and 6 recharging nearly 3 times a day, with each charging session lasts for around 2.4 hours at the charging station. We also examined the fleet-owned charging station performance. A total of 7 fleet-owned charging stations are generated under both separated and semi-shared scenarios. Each fast charging plug serves an average of 4.2 charging sessions under the separated scenario, and it increased to the 4.8 recharging service under the co-located scenario. In a single day 24-hour simulation, the SEV's wait to charge times decreased from 10.7 minutes if they have to build their own charging stations in the separated scenario to just 3 minutes in the co-located scenario. Thanks to the cost sharing and cost sharing strategy, the co-located scenario ultimately lowers the total cost to around $5.9 million and achieves a 16% reduction compared to the separated scenario. And the charging wait time is visualized in the left to illustrate the spatial variations in the EV charging station performance. The darker color here means the longer charging delays. The charging stations are busy recharging the SEVs around downtown Austin and UT Austin campus, with 10 more minutes delay in the separated scenario. Most EV enjoy immediate charging service in the co-located scenario. However, the EVs experience longer charging delay at the public-private charging stations alongside highways, averaging 9 minutes at co-located ones and 18 minutes at the semi-shared ones. So in conclusion, most public-private chargers are added to areas with high trip densities like downtown universities, city parks, and along freeways. The co-locating strategy benefits both public and fleet-owned charging stations. Thanks to cost sharing and avoiding the cost duplication, the total investment cost fall by 10%. And compared to the other two scenarios, the co-located scenario facilitates the shortest average SAV charging delay of around 3 minutes, while providing the immediate charging service for household EVs. For future research direction, the policymaker can explore the dynamic pricing and demand management strategies to mitigate the congestion and encourage the off-peak charging at those public-private charging stations. And fleet operators may consider the fast charging plugs as a promising solution, since it allows the SEV to minimize the downtime for recharging and remain competitive in the ride-hailing market. But it also brings challenges to attract household EV due to higher charging fees. So the fleet operators may try combinations of the level 2 and DC fast charging ports at those shared sites. As new charging stations are generated and added to into the existing grid network, the investigation of the power grid supply and cost and the emissions impact is also necessary. Thank you for joining this presentation, and please feel free to reach out to us if you have any questions.
Thank you so much, Lynn. I understand that it's 10 p.m. at your time.
Yeah.
So thank you. Thank you for staying awake and sharing your research with us.
No
It was again
problem.
very interesting. And yeah, you have actually a applause from one of the audience in the chat box. Lynn, perhaps I can ask one question because I don't see any question in the chat box. So everyone, feel free to start typing your questions or your thoughts. Lynn, I understood that you used the Polaris model to simulate the location. As far as I remember, it's an agent-based or activity-based model. Is that right?
Yes.
Yes. And do you think that can it be modeled with an optimization, traditional facility location problem as well?
Yeah, I think we can achieve this optimization related strategy into this agent-based model. I think that's achievable. Yeah.
Right. So what is the advantage of using Polaris instead of modeling the optimization? Do you consider any heterogeneous behavior from the agents or from the residents in the area or for the vehicles? Or what was the reason that you chose to simulate it with Polaris?
Also, for Polaris, compared with the traditional like four-step model, it can capture some on-demand traveling, and also it can model each agent within the study area, like during the 24 hours.
Understand. So it's
Yeah.
kind of integrated into a strategic transport demand model.
Yes.
So it's not purely just looking at the demand and residents
Yes.
in
Yes.
the
It can
area.
capture this on-demand nature.
Okay, great.
Yeah.
Thank you. And my last question would be, have you published your paper anywhere?
Not yet, but we will publish it soon. Yeah.
Thank you.
Mhm.
Okay, thank you so much. So I don't see any question in the chat box. It was just basically the thank messages. So let's go to the next presenter, Gia. And Gia, I saw you in the room before. Yes. So I can see that you unmuted yourself.
Hello.
So hi. So Gia actually will talk about the static multi-vehicle repositioning problem with electric bicycles. Again, another interesting topic. Gia, would be wonderful if you introduce yourself. What are you studying or what are you at? And over to you.
Oh, sure. Thank you.
Yeah, you can go full screen.
Okay.
Perfect. We have your slides. All good.
Yeah. Hello, everyone. I'm Jia, and I'm from Hong Kong U. And I will introduce you recent work with Professor Sito about the static multi-vehicle repositioning problem with electric bicycles. And I will introduce following these four aspects. First, let's briefly have a look at our background of this study. Bike sharing systems have been emerged as important first or last miles of transportation in all over the world. And in recent years, the number of users of the bike sharing system have been rapidly expanding. And following this trend, the electric bicycles has also been emerged into the bike sharing systems and provide the travelers with multiple choices. And the electric bicycles, which are powered with rechargeable batteries, is regarded as a eco-friendly means of transportation because it's travel with less noise, faster speed, and lower consumptions compared to the conventional bicycles. So it is popular for the short or medium journeys. And it also works as an alternative to private cars and public buses, metros, especially in rush hours, in the traffic jam, I guess. And as we all know, during the past few years, during the COVID-19 epidemic, people have the desire to keep the social distance and such micromobility saw a boost in the ridership. But however, on the other hand, the bike sharing system in the long term faced with the unbalanced supply and demand problem. So we can see piles of bikes in the city corner in many cities. And also with the introduction of the electric bicycles in the bike sharing system, the charging become another fundamental problem. So it is important to desire a strategy for the redistribution and also solving the problem of charging. And this process is what we know as bike repositioning problem, and it has been studied widely in the past few years. It has many categories according to different criteria. But in this study, we only focus on the vehicle-based static bike repositioning problem. It is a variant of the well-known VRP, which proved to be NP hard. So even the simplest vehicle-based BRP is at least NP hard. Current studies on the BRP also focus on some different bike types apart from the conventional bike type. So for example, we can say that there are BRPs with broken bikes, multi-type of bikes, even the electric bike repositioning problem. And it is a pity to find that only one study consider a bike sharing system with both manpower bikes and electric bikes. It is a fleet deployment problem studied by Zhu at 2021. So we can find out some research gaps. First of all, most study focus on the bike sharing systems and electric bike sharing systems separately, but no study combine the both. And also the charging issues have not draw many academic attentions. And also the most of study only focus on satisfying the bike demands, but overlook the potential service failure in returning the bicycles. So our study fill in these gaps by proposing a new bike repositioning problem, considering both manpower bicycles and electric bicycles. And we allow the low battery e-bikes to recharge at the charging stations. To formulate this problem, we propose a MILP model, and the aim is to minimize the total cost. We also investigate several properties of this problem using numerical experiments. I will introduce you one by one. First is the problem. We have 3 types of bikes in total, which are the usable bikes, usable e-bikes, and low battery e-bikes. And also we have 2 types of stations. One is charging stations, another is non-charging stations, and the properties are listed in this table. We also employed a fleet of homogeneous vehicles, and each vehicle starts from the depot, travel among stations to do the repositioning, and finally the vehicle will return to the depot. The objective is consists of several components, and I will introduce later. Here are the parameters, variables, and sets we defined to formulate this arc-flow model. Here is our objective function. We aim to minimize the total cost. The first 2 terms are the penalty cost of unsatisfied bike demand and dock demand. And the third term is the fixed cost, which is regarded as a start-off cost of each vehicle. And the last 2 terms are very common in VRP or BRP studies, which are the travel and loading cost. And here the following are the constraints. We ensure that each station can be only visited once and guaranteeing the in-out flow conservation. And we also ensure that the vehicle put into use cannot exceed the fleet size. And we define the inventory updates on the vehicle as well as at each station, and guaranteeing that the inventory cannot exceed the capacity. We also define the upper bound and lower bound of loading or unloading quantities, and define the update of travel time from station to station. Finally, we define some variables. And let's next have a look at our final part, is the numerical experiment. We want to explore some properties of this new problem. And here are some parameters used in our numerical experiment, and most of them are taken from some related literatures. And we use a instance consists of 7 stations and 1 depot. First, we test the effect of proportion of low battery e-bikes on the cost, and we keep the demand and capacity informations constant, and keep the ratio of usable bike to usable e-bikes to 1. And we vary the proportion of low battery e-bikes from 10% to 50%. And in this process, there are less and less usable bikes and e-bikes in the system, so they are not available to satisfy their demand, so lead to a higher bike deviation. And then we also test the effect of number of low battery e-bikes on the cost. And in this case, we keep the total number of usable bikes and e-bikes at the system, and increase the number of low battery e-bikes at each station. In this case, the total number of bikes in the system also increased. So due to the limit of vehicle capacity, the redundant bike cannot be collected properly. So the dock deviation penalty will be increased. And at the same time, there are less vehicle capacity available to transfer the usable bike types to satisfy their demand. So we can say a slight increase in the bike deviation as well. Lastly, we test the effect of proportion of usable e-bikes. Oh, I don't know. From a relative low level to a relative high level, say 10% to 19%. And we, at the same time, we keep the proportion of low battery e-bikes at each station constant at 10%. And in this case, we can find that on the two sides of this curve, one usable bike type is abandoned, another is in shortage. So the abandoned bike type is still surplus, even it satisfies all its demands, and the redundant cannot be collected properly due to the capacity limits. And the usable bike type in shortage is not enough to satisfy its demands, and because of the lower supply. So on the two sides, both of the bike and dock demand is higher than the case in the middle, when the two bike type of usable is similar. The repositioning work can also can address the both bike demands, and collect or transfer the abandoned bikes as many as possible. So the whole curve presents a U shape. At the same time, we can say that the workload in the middle is higher than the case on the two sides. So the loading cost curve present an inverse U-shaped. This is quite interesting. So here are the summary of our conclusions. I don't know why it is jump. So this conclusions also highlights the importance of bike repositioning. And to conclude this presentation, I first introduced the background and also the motivation of this study, and we find out some research gap from the literature review briefly. And then we formally proposed our problem and our mathematic model. And finally, we investigate some properties of this new problem. And the future studies involves designing some effective algorithms for solving the large-scale networks. And also we can consider more bike and battery features such as different battery level or charging rates. And we also aim to use different rebalancing or charging methods such as battery swap or battery covenants to do the rebalancing. So thank you for watching.
Thank you so much, Gia. Again, another interesting research. So let's see if there is any question. Please feel free to ask your questions. But meanwhile, maybe Gia, I can ask you the first one. It's very interesting actually for modeling the e-bike redistribution in a city with an optimization model. I never thought about that. I was just wondering whether you also considered the so when you are talking about redistribution, it means that they will be redistributed by a truck or by another vehicle, right?
Yeah.
Yes, because if they're low battery, then you can't really ride them back to a depot. Is that
Yes.
correct?
Yes.
Yes.
Yeah. Correct.
So I'm just wondering if in Hong Kong there is any, application or basically product for e-bike sharing or not. I'm not really aware in Sydney or in Australia.
Yeah, but in Hong Kong, to be honest, there are not many bike sharing systems because of the geography. So we normally use the data from City Bike in US, New York, or the data in mainland China. The database is enough and interesting. So we normally didn't use a lot of Hong Kong data.
Yeah. Well, in Brisbane, I remember that there was a big launch of e-scooters and e-bike sharing scheme. I think it was offered by two companies. I don't remember. Do we have anyone from Brisbane to talk about the e-bike sharing applications? Okay, perhaps not, but yeah, I think Brisbane actually could be one of the very good use
Yeah, that's
cases.
true.
Great. Okay, so I don't see any questions. Please, again, feel free to continue asking your questions in the chat box. If not, perhaps we can go to the next presenter, Anna. And I have Anna's bio. So Anna Luiza Santos Disa is a final year PhD candidate in transport engineering at the University of Melbourne, Australia, supervised by Dr. Patricia Lavari. And her PhD research focuses on the relationship between travel time use and activity travel behavior in the Australian context. So Anna, yep, please go ahead and share your screen.
Thank you, Anna. Thank you for the presentation. I'll share my screen now.
So while you're sharing, thank you. Okay, oh good.
Can you see
So
it?
over to
Yeah.
you. Yes,
Thank
you
you.
can go full screen and I hand it over to you.
Oh, good. So I'm Anna. I'm supervised by Dr. Patricia Lavieri, and I'm also co-supervised by Dr. Yesig Pollock from Imperial College London. And today I'll be presenting our work titled Travel-Based Multitasking Reframed, a latent class cluster analysis to identify travel time use styles. So I think this is probably the only study that's not about electric mobility. Actually, it's about like travel time use. So I'll start with the motivation is that multitasking, which has become a ubiquitous behavior in our society, and is primarily facilitated by information and communication technology. So more than 95% of the population multitasks daily, and that could add, for instance, more than 3 hours to our daily budget. So multitasking was introduced into transport research through the study of travel time use. So travel time use refers to undertaking activities during our daily journeys. And there are like many other terms that are utilized, adopted interchangeably with travel time use, such as multitasking while traveling and travel-based multitasking. In this current study, we will adopt different definitions. So we consider that travel time use refers to the act of undertaking activities while traveling. So we don't utilize the terms multitasking because we believe that it's not always the case that undertaking activities while traveling is multitasking. For instance, if you are traveling by public transport or like in a train and you are undertaking activities, potentially the act of traveling is less of an activity and more of the environment or the background where other activities can occur, so not necessarily multitasking. So in this current study, we actually utilize the term travel-based multitasking to refer to the act of undertaking 2 or more cognitively demanding activities simultaneously. So for instance, a person who is working and listening to music or taking care of another passenger, for example. So travel time use received a renewed interest in the past 15 years, so especially to understand the effects of information and communication technologies on activity travel behavior, and also to understand how travel time use could affect activity travel behavior. For instance, travel time use could affect travel behavior by influencing the choice of passenger rides and modes, like public transport and automated vehicles. It could also influence the decreases of the value of travel time savings, which translate into people being less resistant to travel longer journeys, and could also influence transport investments in a sense of should we invest in shorter travel times, or maybe should we invest in making the travel time more worthwhile for the traveler? So that's another impact. And lastly, travel time use could also influence the organization of daily activities. For instance, if a person transfer an out-of-trip activity into the journey in order to release time during the day, and then by releasing time, they could undertake all the activities that might require travel, for example. So that's like some of the implications of travel time use for activity travel behavior. So in the current study, what we will investigate is we will investigate travel time use styles. So we utilize this term to refer to distinctive patterns of engaging activities while traveling. And the first the specific objective is to investigate travel time use style from the perspective of 4 indicators. So we have first activity transferability, which refers to transferring activities from outside of the journey into the journey in order to release time during the day. Secondly, travel-based multitasking, as we define in the current study, undertaking 2 or more simultaneous activities while traveling, just referring to the activity level, regardless of how the individual is traveling. Thirdly, we have activity participation, the choice of discretionary, maintenance, and mandatory activities. And lastly, ICT-related information, also internet access while traveling, and carrying a laptop or tablet during the journey. The second specific objective is actually to identify the profile of travelers and travel context characteristics associated with each one of the travel time use styles. And we operationalized this study by implementing a latent class cluster analysis. So the LCCA has 2 submodels. One is the measurement models, which takes the indicators of the travel time use styles, as I mentioned. So there are 4 types of indicators, which actually translates into 7 qualitative indicators. And the other model is the structural model, the class membership model, in which we understand what are the characteristics of the individuals and the travel context associated with each one of the travel time use styles. So as covariates, we have, for instance, social demographics, psychosocial characteristics. We have 5 constructs which were factor analyzed and entered exogenously. So we have like polychronicity, which refers to the preferences for multitasking, filling breaks and waiting times with activities, preferences for faster journeys, which refers to is a measure of the dislike of traveling, perceptions about the usefulness of travel time, and time pressures as well. We also have physiological characteristics, so motion sickness in the main mode. And then we have the travel context, which takes as variables the main mode choice, trip purpose, travel companion, and total travel time. So in terms of the data we use data from an online survey that was collected last year here in Greater Melbourne and Geelong. So we collected a representative sample of the adult population in this area here in Australia. It's representative in terms of age, gender, and income. And our sample size is like roughly around 1,700 respondents, which is above the minimum required sample size we calculated of around 900 responses. So here, the behavior of interest, travel time use, has this incidence in our sample. So 29% of our sample did not engage in activities while traveling. So they are treated as an exogenous class in our study. We will characterize them, but this subsample is not included in the latent class cluster analysis. And then we have like 71% of our sample who engaged in travel time use, which is the sample we conduct the latent class cluster analysis. Now I'll present the results of the LCCA, first starting with the measurement model. So we identified that the best model would have 4 clusters, and we characterize these clusters in this way. So the first one, the largest clusters, we call them time passers. So they comprise 38% of travel time users. And we call them time passers because they primarily engaged in discretionary activities and primarily in listening to music. So they likely did that just like to pass time, to make the journey a little bit like more bearable for them, like decrease the disutility of travel time. They did not engage in multitasking, so they conducted sequential activities, and they primarily did not transfer activities from outside of the journey into the journey to release time. The ICT-based effective multitaskers, so the second clusters on the other hand, so they have they form 32% of travel time users. They were called this in this way because they engaged in multitasking while traveling, so 75% engaged in simultaneous activities, mostly transferred from outside of the journey, so 86% engaged in activity transferability. And primarily those activities were ICT enabled, so because they have engagement in ICT, so 93% of them accessed the internet while traveling. And interestingly, they had multi-activity participation, so they engaged in different activity types while traveling. So we have like 98% in discretionary, 72% in mandatory, 71% in maintenance activity. The upkeepers, which form 18% of travel time users, they were called upkeepers because they primarily engaged in maintenance activities and mostly in companion-related tasks. So tasks like, for instance, taking care of another passenger. These travelers engaged primarily in sequential and non-transferred activities. The last cluster of the LCCA model was called heavy working investors. They comprise 12% of travel time users, and they engaged 100% in mandatory activities and primarily privacy-sensitive work tasks, for instance, having taken a phone call for work purposes. They engaged primarily in sequential activities, so no multitasking, and these activities were not transferred from outside of the journey. Sorry, okay. Now the class membership model. So I will also present the characteristics of the exogenous class of no travel time users, but starting here with time passers. So the characteristics of time passers are as follows. So they are primarily older travelers aged above 44 years old, so from the Generation X and baby boomers, and live in middle income households. In terms of the psychosocial characteristics, what stood out was that they had stronger preferences for faster journeys, which is a measure of the dislike of travel. So this is why we believe they engaged in discretionary activities to decrease the disutility of travel time. In terms of the travel context, they travel primarily by non-passengerized mode. So they had, for instance, to drive a car or to cycle. and they tended to have shorter journeys below 30 minutes. The ICT-based effective multitaskers have a very different profile. So they tend to be younger travelers from the generation Z and millennials, and they are like primarily students. Regarding the psychosocial characteristics, they tended to be more time pressured. So we believe that this is one of the drivers, so one of the motivations why they have to engage in these travel time user styles. But they also have they have more positive perceptions that the travel time is useful as well. So this is the Seoul cluster that had a higher percentage of passenger rising modes. So they tended to travel by public transport and car passenger options, which tend to facilitate a larger pool of activities. And they also tended to have longer journeys. The third cluster, upkeepers, they were primarily women who are currently not working. And similarly to time passers, they had stronger preferences for faster journeys, meaning that they also had a strong dislike of traveling. They tended to travel primarily by non-passengerizing modes and with a companion, which makes sense because they primarily engage in companion-related activities like taking care of another passenger. The fourth cluster, heavy work investors, they were primarily middle-aged individuals with higher education and income levels. We didn't see any psychosocial constructs stand out. They were somewhat in between the no travel time users and ICT-based effective multitaskers in terms of psychosocial constructed scores. And regarding the travel context, they travel primarily by non-passengerizing modes, which is also an interesting result because it's saying that private modes like car can be a time-space locus for work activities. And it also makes sense because they engaged in privacy-sensitive tasks like taking a phone call. So the environment of a private car can better accommodate those activities. And also tend to travel alone. Regarding the exogenous class of no travel time users, they were primarily older travelers with lower education and income levels. And interestingly, they had lower score in all psychosocial constructs. So for instance, they have a very low score in preferences for faster journeys, meaning that they don't have much of a dislike of traveling. And they likely don't engage in travel-based activities like to decrease this disability of travel time, for example. Their travel context is as follows. So they primarily travel by non-passengerizing modes, and they also had like shorter journeys. So in terms of conclusions, we can see that in terms of transport implications for transport appraisal, we see that very similar for time passers and upkeepers. So they like these two classes, they might be less sensitive to investments aimed at facilitating travel-based activities. Instead, they might benefit more from traditional policies aimed at decreasing travel times. For the other two classes that we identify, so ICT-based effective multitasking and heavy work investors, we see more implications for instance, in-vehicle designs and facilities of public transport modes and future automated vehicles. In the case of ICT-based effective multitasking, what we see is that both public transport and future AVs could invest in an in-vehicle design that enables a multi-purpose usage of travel time and also an ICT-enabled travel time. So for instance, it might be important for these travelers to provide them with an internet connection or power sockets where they can charge their ICTs. For heavy work investors, what we see is that if they are deprived from the opportunity to work while traveling, it might affect like their travel satisfaction and choices. So for instance, if they cannot work while traveling, they could, in this case, prefer having like shorter journeys or even prefer like telecommuting altogether. What we see for implications for AVs for this current cluster here is that we see that there's a lot of research on the conduciveness of AVs for like work activities in the future. And what we see is that AV adapted for work activity might be just the case for a small share of travelers, as we see in our current study. So maybe like around 8%, 8 to 12% is that what we identified here. And lastly, for no travel time users, what we conclude from them is that they might not have strong intrinsic or extrinsic motivations to engage in travel-based and multitasking, and also that their travel context might not enable travel-based activities as well. So thank you for your attention. We have this study is currently not available. It's under review, but not available online. But we have another interesting study about activity transferability, which is one of the indicators we use in this study. And as it is primarily a EV section, we also have a study on demand management for electric vehicle charging study, which is currently published if you would like to check it out. Thank you very much, and I'm open for questions. Thank you.
Hi.
Sorry.
Okay. Thank you, Anna.
Okay.
Yes, I was muted. Sorry.
Sorry.
Same, right? Always. Yeah, so thank you so much for your sharing actually your exciting and interesting research with us. I can see there are two questions. First one is from Professor Yamamoto, who is suggesting that looking at the membership function, a person may change the cluster or the class to belong to one of these depending on the occasion or time to time. So do you have any anything to add to that? How was the probability of the class membership and like from with the same person, different trip purposes, how actually do you reckon that there are overlap between classes or they're kind of shifting from one class to another class?
Yes, so it's a very interesting question, and we collected. So this data that I utilized was for the outbound journey, and I do like put in the conclusions that we believe that might change if we take a look at the inbound journeys, for example, during the outbound journey. So when people are going to work, they tend to engage more in work activities, for instance. So we believe if we analyze like the inbound journeys of people coming back from work, the sizes of the classes might change, I believe, and potentially we might have different classes as well. So yes, I believe it will change. Yeah, for sure.
Okay, thank you. So the second question is from Jian. Jian, feel free to unmute yourself and ask the question if you like.
Okay. So my question is about because I think now with ICT, where activities are super fragmented, right? So 1 minute you're using Instagram and then you're replying to an email, you're at Twitter, and then you're buying something on Amazon. So I think there's a lot of challenges to measure like activity use, especially when using web service or more passive service that the respondent has to specify, right? So I was wondering how do you deal with that in the data collection part and also in the analysis part?
So the fragmentation part, because we did like have this indicator of activity transferability, which can be referred to as an indicator of activity fragmentation, but it's just like fragmenting the activity from outside of the journey into the journey. So it's one measure. But I think a very good way would be, for instance, on how to deal with that in terms of data collection would be like maybe using smartphone-based data collection. The way we collected, it was a survey. So we collected more in terms of time allocation and not specifically the sequencing of the activities. So yeah, I think the indicator we have of fragmentation is this activity transferability one.
Thank you.
Interesting. Thanks, Anna. I'm aware that Professor Taha Rashidi in our center, they have a smartphone application, and one of his PhD students, Malihe, is looking at the basically the value of time by using the trajectories of the smartphone, and then also asking the smartphone phone owners basically to also kind of report and confirm their activities and what they have done, etc. So I reckon that could be a very interesting collaboration. So please reach out if you'd like the contacts. I'm sure that Patricia also knows Taha, so definitely I can make the introduction.
Thank you very much. Yeah, that's very interesting. Thank you.
Amazing. Okay, good presentation. Thank you so much. And let's just go to the next presenter. Thankfully, actually, we have enough time even for a short break before the next session. So the next presenter, I reckon we have Ding in the room. The next presentation will be about eliciting Singapore ride-hailing drivers' preferences for electric vehicles on certain electricity prices, an eye tracking study. Interesting one. So Ding, please unmute yourself and start sharing your screen. Hopefully everything works on your end.
Thanks, professors. Yeah.
Yes. So you can go full screen. Awesome. We have your presentation. So if you don't mind, Ding, if you introduce yourself first, that would be wonderful. Thank you. Over to you.
Sure. Thanks, Professor. So my name is Ding Jiaxuan from National University of Singapore. Currently, I'm a PhD student under the supervision of Professor Pratik Bansal. So thanks for attending this session. So the topics we're going to talk about today is eliciting Singapore ride-hailing drivers' preference for electric vehicles under uncertainty electricity price and tracking study. It's a quite long title, but no worry, we'll tell anything clear step by step. So to start with, in our research, we consider two types of vehicle. One is conventional vehicle, referred to as fully powered by gasoline, diesel, or natural gas. Another is the electric vehicle. Here we refer to this vehicle fully powered by electricity. Since most of the major economies have committed to achieve the net zero emission goal by the middle of the century, it's quite important to understand that how drivers are choose between conventional vehicle and the electric vehicle. So from this plot, we can tell that one of the most compelling advantages of EV is relatively low operating cost compared to SCEV. As a result, when decided between EV and conventional vehicle, drivers tend to weigh the potential saving in operating cost against the additional cost of renting or owning an electric vehicle. Well, this operating cost is closely tied to the electricity price, which is generally being subsidized at the current stage. However, this subsidy kind of brings the uncertainty in the operating cost in terms of its duration and amount. As we can imagine, though, once the electricity price goes up, the advantages of saving operating costs decrease, and the EV preference will also diminish accordingly. But the experience from UK have already told the story. It's like when their electricity price almost doubled, their EV preference almost halved. Given that Singapore is still at the starting stage of promoting electric vehicles, it's kind of important for us to understand that how does uncertain electricity price would affect Singapore ride-hailing drivers' preference towards electric vehicles. Well, second, we will talk about the eye tracking. So here, this plot is a typical setup for an eye tracking experiment with this top eye tracker. So this eye tracker in front of the respondents was equipped with a high-speed camera that can automatically record people's eye movement after proper calibration. Since the eye tracking technology allowed us to have people's eye movement data in sequence, it can help us to some extent to infer their attention. So this plot is a heat map generated based on the fixation duration. Basically, the color is the longer time respondents are look at these attributes, the more significant, the more important these attributes will be towards the respondents. Since in the eye tracking experiments, we require respondents to come in our lab to answer their questionnaire. So generally, it takes more time and financial cost compared to the online experiments. Therefore, most of the eye tracking experiments have suffered from the relatively low sample size. compared to the online experiments. So in light of this, we put forward our second question. Is it possible that we can infer the attention from the eye tracking data to improve the model fitting of the online dataset that without the eye tracking information? So based on these two questions, we make the following contributions. So first, we'll design stated preference for electric vehicle preference under uncertain attributes. And second, we'll try to identify a suitable modeling framework that can both capture the preference under uncertainty and incorporate the dynamic of the eye tracking data. And finally, we will find if it's possible to transfer the insights from the eye movement to improve the model fitting of the online dataset. So first, we will talk about the experiment design. Since no one have explored to design a stated preference to understand EV preference with uncertain scenarios. So to make the experiments realistic while avoiding the dominated alternative, we kind of split our experiments into two parts. So in the first part of the experiments, respondents was asked to indicate the electric vehicles renting cost their willingness to pay. And in the second part of the experiments, we will bring in uncertainty in the daily operating cost of the EV. The respondents was asked to choose between conventional vehicle and electric vehicle based on the monthly rental cost, daily operating cost, and the driving range. The attributes value of the conventional vehicle is purely estimated based on their currently rented vehicle characteristics. Well, for the electric vehicle, the monthly rental cost was indicated by respondents, and the driving range was estimated based on the average EV performance compared to the conventional vehicle. To bring the uncertainty in the operating costs, we manually separated two states. So state 1 indicates the current state where the subsidy remains, therefore it will have lower daily operating cost. And state 2 referred to the future scenario where the subsidy was kind of being cancelled later, so it will have a higher operating cost compared to the base operating cost. Moreover, we ensure that the probability of these two states are summed to 1. We conduct the same experiments in both lab-based eye tracking experiments and street intercept online dataset. So it's kind of give us the foundation to transfer the insights from the lab-based eye tracking experiments to the broader online dataset. So for the modeling methodology, here we consider two modeling frameworks. One is statics, another is dynamic. So here when we say statics, we refer to those models that only focus on the final choice outcome while ignoring the dynamic nature of the decision-making process. So first we will talk about the most commonly used statics model to capture the decision under uncertainty, which is the multi-attribute cumulative prospector series model, MCPT model. Well, you can tell from its name, it's prospector series. So it assumes that people's preferences are formulated based on the prospectus value of the alternative. Therefore, it's a function of attributes value and corresponding probabilities. And moreover, MCPT model assumes that people evaluate alternative based on the reference point. Therefore, the attributes value that more favorable than the reference point are treated as a gain. Otherwise, it's treated as a loss. Besides, CPT model also assumes people have this aberration, means that they're more sensitive to loss compared to gain. And second framework we use is decision field theory model, DFT model. It's a dynamic model that assumes people's preference are gradually accumulated over time. Here's the plot to kind of show how their preference are dynamically accumulated over time. So for DFT model, the accumulation direction and amount of evidence accumulated at each stage is strongly decided by the weighted memory and comparison at the current stage. To be more specific, DFT assumes that at each stage, respondents only pay attention to one single attribute. What they do is they will comparing across alternatives based on the single attribute dimension. And at that stage, they may switch their attention to other attributes. So this process will repeat again and again until one of the alternative accumulate more preference that will become the chosen alternative. So this is the modeling framework of the original DFT. So original DFT assumes that people's attention are equally distributed towards each attributes. Since we have the eye-tracking data at hand, so we are thinking, is it possible for us to revise the DFT framework to incorporate both uncertainty and the attention? So what we do is we will calibrate this attention weight matrix by making the following assumptions. First, we assume that higher fixation frequency on the attributes dimension signify great importance of the attribute dimension. And second, we assume that the daily operating cost days with a higher probability are more likely to be considered by the respondents. And finally, we assume that the online dataset and the lab-based datasets have similar attention distribution for each choice scenarios. This kind of gave up the foundation to transform the insights from the lab to the online datasets. Besides, based on this revised framework, we also tried to consider the decision heterogeneity by incorporating it into a latent class framework. So in a latent class framework, it assumes that peoples can be classified into different groups based on their demographic attributes or attentional or attitudinal questions. So the probability of choose alternative I is strongly controlled by the probability of respondents belong to the specific class and the conditional probability of choose alternative given the parameters in the specific class. So finally, we will see how the results can answer the two questions we raised before. So in total, we have 40 respondents came in our lab to conduct experiments and over 150 respondents answered the online experiments. So their summary statistics are summarized in this table. From this table, we can tell that they have relatively similar demographic distribution, which indicates the potential of transforming the insights from the lab-based eye tracking dataset to the broader street intercept online dataset. Second, we'll talk about the modeling performance. So from this table, first conclusion we can see clearly is that the DFT model outperforms MCPT model in fitting the observed dataset. It can reduce the BSA value by around 100 points compared to MCPT. Second, we can see that if we can calibrate the attention weight matrix with the real eye tracking data, it can improve DFT's fitting performance. It can reduce the BIC by around 20 points. And finally, we can see that if we can extend the DFT in a latent class framework and also calibrate it with eye tracking data set, we can substantially improve the model fitting, which indicates the importance of considering the preference heterogeneity when modeling the decision under uncertainty. Then we will have a more detailed look at the latent class DFT model with eye tracking data. So from this table, summarize the sign of the parameters. So first conclusion we can see is that people who drive less distance or less or few number of days are more likely to choose conventional vehicles compared to electric vehicles. It's reasonable under Singapore context because for those drivers, they drive less. Therefore, the potential saving in operating costs cannot offset the extra amount they pay to rent an electric vehicle. And second, we can see that for early adopters and people with less experience, they are more likely to choose electric vehicle over conventional vehicle. Besides, we also found that these less experienced drivers are those younger drivers. Therefore, we can conclude that the younger, frequent long-distance drivers are more likely to choose electric vehicles compared to SEV. Finally, we try to provide some policy implications that can ensure the EV preference under uncertain operating cost. To do so, we draw the following two plots. So here, this plot is under high uncertainty scenarios, and this plot is under certain scenarios. The x-axis represents to the increase in state 1 operating cost compared to the base operating cost, and the y-axis represents to the increase in state 2 operating cost compared to the base operating cost. The dashed line and different color represents to the probability of choosing electric vehicles. To be more specific, we would like to see 2 points, A1 and A2. So A1 represents to the scenarios that there will be 50% probability the operating cost will be 10% higher, and 50% probability the operational cost will be around 35% higher. And for the A2, it represents the scenario where the operating cost will have 99% probability to be around 22% higher, and only 1% probability to be 30% higher. By comparing these two points, we can draw the conclusion that if the increase in the charging price are likely to be small, say around 20%, it's better to let the drivers know in advance instead of let them guess and uncertain about the amount of increase in daily operating cost, because letting them know was more efficient. So just to briefly summarize what we do in the study. So we make the first attempt to investigate Singapore ride-hailing drivers' preference for electric vehicles under uncertain electricity price. Our model performance results shows that DFT outperform MCBT in capture decision under uncertainty. While tracking data and the latent class framework can further improve DFT's model fitting. And from the parameters, we can conclude that the younger, frequent long-distance drivers are more likely to choose EV compared to ICEV. Finally, we can conclude that if we want to ensure the EV adoption rate is suggest to inform drivers about the small expected changing in charging cost can help to ensure the EV adoption rate. So this is the end from my presentation. If you are interested in our paper, you can have the access to our paper online. If you have any questions, just feel free to let me know or drop me via the email. So thanks all for your attention then.
Thank you, Ding. Again, very interesting and complete, actually, piece of research. Thanks for sharing it with us. So I can see that Jian has a comment. Jian, again, feel free to unmute yourself.
Okay. Thank you for your presentation. Nice to meet you again. So I have 3 questions that I already posted in the chat, but I understand that
yeah, sure.
you transfer the daily operation. You can transfer the daily operation cost to the online case from the I experiment. But how do you do it with the fixation frequency? Because I understand that you can estimate that at the individual level, right? That ratio of where they're looking at. But in the case of the online case, because they're different individuals, so do you assume that the weight matrix W is just the average for all the users?
Yeah, at current stage, we do not use the individual attention level. So here our attention level is per scenario. So in total, we have 10 scenarios. So we will have 10 scenarios in the lab and 10 scenarios on the online experiment. So we will transfer the choice-based attention to the online data set. We do not consider the individual things at the current stage.
Okay, thank you. And then the other one is about the goodness of fit, right? So are these in sample or out of sample? Because the difference is not that big, so they may actually change if you do it out of sample. So
yeah, currently we only consider the in sample. We do not conduct the out of sample yet. But thanks for the suggestions. We will consider the out of sample in the next stage.
Okay, and then finally it's about the policy implications, which I think were very interesting. You showed those 2 plots. But are the implications different from the prospect theory model and the DFT?
We do not try the MCPT. So this plot was drawn by the best fitting model, the latent class DFT with eye tracking data. Yeah, but yeah, it's quite enlightened. Yeah, maybe we can show the implications of based on the MCPT other.
Very interesting, because if your contribution is methodological, right? Ultimately, you want to link it to policy implications. So they're actually very different, and that's a very massive contribution, I would say.
Yeah. Thanks for the suggestions.
Yeah, I actually second Jian that perhaps the in-sample goodness of fit can show you that how your model has been, fitted to your observation data that you use for the modeling purpose, but just for for the outsample goodness of feed, it kind of shows that for the whole population, perhaps how does it work, and would be interesting actually to compare the out of sample. Thank you. And also, I had another question that Jian also is kind of relevant to the answer that you gave it to Jian. Let me read Gina's question. So Gina, okay, Gina, I can ask the question, but also you feel free to unmute yourself. So the question is, Gina thinks that young, frequent, long-distance drivers are more inclined to adopt EVs. Your conclusion is better to define the long distance in this sentence. Otherwise, it sounds strange that long-distance drivers are likely to adopt EVs. And are they really worried about charging?
Yeah, thanks, Gina. Thanks for your questions. Yeah, it's because I conclude that this is more like the Singapore context, because for Singapore context, most of the ride-hailing drivers like they drive around 40 kilometers per day at most, because therefore, given this daily driving distance, most of the major EV mode that can satisfy their daily traveling commute satisfactions. So that for in Singapore context, most of the drivers will not that worry about the charging
Distance
or
anxiety.
not at the current stage. Yeah, thanks for that.
Yeah. The distance range anxiety actually is would be very relevant to the context of the study, as you mentioned,
relevant to the
Singapore.
context.
Yeah. Perfect. So perhaps that. And thank you for sharing the QR code with your SSR and paper, the draft paper. So I assume that you have submitted to a journal. Is that right? Or are you planning?
Yeah, we've
to
already
submit?
submitted. Yeah.
You have already submitted. All good.
Yeah.
Thank you so much, Queensland. And it's going to be on intelligent transportation systems, analysis, and technologies. So we will start in about 17 minutes, but that's really good that we have a break, short break. So please just do a bit of a stretch, pour a cup of coffee or tea for yourself and come back to the same room. So we will stay actually in the same room. I will unmute myself, and also I'll stop my video, but I will be around, and everyone also will be around. So thank you so much for tuning in for the first session and the first day of BTR.